Howdy. Albert Einstein was quoted as saying that a theory is the more impressive the greater the simplicity of its premises, the more different kinds of things it relates, and the more extended its area of applicability. Therefore, the deep impression that classical thermodynamics made upon me. It is the only physical theory of universal content which I am convinced will never be overthrown within the framework of applicability of its basic concepts. And so I think what he's saying here is that thermodynamics has a really wide range of applicability, is very firm in its foundations, and is not going to be changed in the framework of its applicability. This video is on the first law of thermodynamics. Using the first law of thermodynamics, how much heat is transferred to or from a system can be calculated. The first law says that the change in internal energy of a system is equal to the heat added to the system plus the work done on the system. Often people interpret the first law to mean that energy is conserved. And so if you assume that the universe is a closed system, then that would mean that energy is conserved. And so after watching this video, you should be able to describe how energy can be converted from one form to another form and yet is conserved. You should be able to describe how the universe can be separated into a system plus its surroundings. You should be able to calculate the change in internal energy of a system from the amount of heat added to the system and the amount of work done on a system. You should be able to describe what enthalpy is. You should be able to describe how enthalpy and internal energy are both state functions and what it means for them to be state functions. And you should be able to describe what it means for a process to be exothermic or endothermic. And so energy is the capacity to do work or transfer heat. Some forms of energy include heat, light, electrical, kinetic, and potential. Temperature is a measure of kinetic energy at the atomic level. And so if you remember, for gases, the average kinetic energy of a gas is equal to 3R2 over 2N, where R is the gas constant, T is temperature in Kelvin, and N is the number of particles. And so all gases at a specific temperature will have the same exact average kinetic energy.
Heat, or thermal energy, is associated with the motions of atoms and molecules in a substance. The more rapid these atomic scale motions, the greater a substance's thermal energy and the hotter it is. When we plunge a hot metal bar into cool water, thermal energy from the bar transfers to the water. While the atoms and molecules of the bar slow down, those of the water speed up. The transfer of energy can be measured as a rise in water temperature.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
And so heat will transfer from the hotter object to the cooler object if they are in thermal contact. Now, the zeroth law of thermodynamics was developed after the first three laws of thermodynamics, but is considered more fundamental, and so is labeled the zeroth law of thermodynamics. And the zeroth law says that if two objects are in thermal equilibrium with a third object, then the two objects are in thermal equilibrium with each other. And so to me, what the zeroth law is actually is defining the concept of temperature. And again, it was developed after the first three laws, but is considered more fundamental, and so it's labeled the zeroth law. And so we consider energy being conserved, but it can be transformed from one form to another form. And so kinetic energy is the energy of motion. It's equal to 1/2 mv squared, m being mass and v being velocity. Now, potential energy is the energy due to the position of an object. And so by the diver climbing the platform, he's converting kinetic energy into potential energy. And then once he jumps, he's converting that potential energy back into kinetic energy. And so energy is conserved, but it can be transferred from one form to another form. Now, just like there is potential energy with a diver, based on its position, there's also chemical potential energy, which is analogous. And so less stable compounds have a higher chemical potential energy, and that chemical potential energy can be converted into something, say, like heat. And so energy can be transformed amongst different forms. Total amount of energy is constant. And so if we think about a boulder rolling down a hill, initially the boulder has high potential energy. It can roll down the hill, converting that potential energy into kinetic energy. And so the difference between potential energy initial and final is going to be exactly equal to how much kinetic energy the boulder gets at the bottom of the hill. Likewise, we can push the boulder up the hill, converting kinetic energy into potential energy. Now we'll have to add as much work as the difference between the initial and the final positions. Again, energy is conserved. It's just transferred from one form to another form. And so we can think about potential energy to kinetic energy, boulder rolling down a hill. We can think about chemical potential energy to heat. So if we burn a fuel, again, fuels will have high chemical potential energy. The less stable something is, the higher its chemical potential energy. Heat to chemical potential energy. So if we have a liquid and we heat it to a gas, chemical potential energy to electrical energy. That's how batteries work. Electrical energy to chemical potential energy. And so if we do electrolysis of water, we're actually produce something less stable. And so we're converting electrical energy into chemical potential energy. And so in all these instances, energy is being transferred from one form to another form, but the total amount of energy is not changing. And so we can look at this example and wonder, from what form to what form is energy being transformed?
A buffered luminol solution with a copper-2 catalyst is added to the funnel on the left. A hydrogen peroxide solution is added to the funnel on the right. On releasing the rubber tubing, the solutions mix. The chemical reaction generates energy which is seen as blue light. This process is chemiluminescence. When the reacting solution mixes with a dye, fluorescein, the light energy from the reaction causes the fluorescein to give off a greenish light in a process called fluorescence.
And so simply we're converting chemical potential energy into light. And so we can look at this one.
Potassium chlorate is sprinkled on a small mound of red phosphorus. A gentle tap with a hammer causes the mixture to explode.
And so we're converting chemical potential energy into heat and light. Again, the less stable a compound, the higher its chemical potential energy.
In this experiment, we are looking at the explosive decomposition of a compound of nitrogen triiodide. This brown compound is so sensitive when dry that just touching it with a feather causes an explosive decomposition. It forms nitrogen and iodine. Like this mousetrap, which releases potential energy from the spring, the nitrogen triiodide releases chemical energy. When it decomposes into its elements, nitrogen and iodine.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
And so again, the less stable a compound, the higher its chemical potential energy. So explosives, fuels all have very high potential energies. Now here what we're doing is we're converting chemical potential energy into kinetic energy of those particles. And again, you can convert energy from one form to another form, and still the total amount of energy is conserved. Now we can think about the universe as being composed of two parts, a system and the surroundings. And so you can imagine if you're doing a reaction in a beaker, the beaker would contain the system and the surroundings would be everything else. Now we're going to define the system as being a closed system, meaning that no matter can go between the system and surroundings, only heat and work. And so that's going to be a fairly important definition. So again, the way we're defining this is that the only thing that goes between the system and surroundings is heat and work. Now we can write down the first law of thermodynamics as delta U equals Q plus W. And so delta U is the change in internal energy. Q is defined as the amount of heat added to the system, and W is defined as the amount of work done on the system. And so if heat is added to the system, then the internal energy of the system will increase. If work is done on the system, then internal energy will also increase. Now, if heat goes from system surroundings, then the internal energy of the system will decrease. And if the system does work, then the internal energy of the system will decrease. And so the change in internal energy is just going to be internal energy final minus internal energy initial. And so again, if delta U is positive, that means internal energy of the system increased. If Q is positive, heat was added to the system. If W is positive, work was done on the system. And so if 5 joules of work is done on the system and 3 joules of heat is emitted by the system, what is the change in internal energy of the system? And so delta U equals Q plus W. And so 5 joules was done on the system. So that means W is plus 5. So again, remember, W is work done on the system. And 3 joules of heat is emitted by the system. And so Q is the amount of heat transferred to the system. Here we're having heat leaving the system. And so that's going to be a minus 3. And so delta U equals Q plus W. So delta U is equal to minus 3 plus 5. And that would give us plus 2. So the internal energy would change by 2 joules. Another example, we can consider the bag here as our system. And so we can put dry ice in it, and the dry ice can actually change into CO2.
Solid carbon dioxide vaporizes in an endothermic process as it absorbs energy as heat from its surroundings. If the CO2 is in a sealed non-rigid container, such as a plastic bag, the absorbed energy performs 2 functions. It vaporizes the solid and provides the energy for the expanding gas to perform work by moving objects such as a book or the molecules of the surrounding atmosphere.
So a question we could ask is, okay, so was Q for this process positive or negative? Well, if you want to go from a solid to a gas, you always have to add heat. And so heat was added to the system, and so Q would be positive. Now, is W positive or negative? Well, the bag lifted that book, and so the system is the bag, so the system did work. And so in this case, W is actually negative. And so Q and W can both be the same sign, can both be positive, can both be negative, or they can be opposite signs. So in this case, Q is positive and W is negative. And so, there's a few different types of work. There's expansion work, weightlifting, electrical. And we saw that, the book lifting, that would be weightlifting. And so that'd be equal to mass, acceleration due to gravity, and change in height. And the one we'll be most concerned about is expansion. And so expansion work is equal to minus P delta V, where P is the external pressure and delta V is the change in volume. And so if we have a piston, and if the piston expands, then your delta V would be positive because you have a negative there. That would give you negative W. And so if this piston is our system and it expands, then the piston's doing work and W will be negative. If we push on the piston, so the delta V gets smaller, that would be negative. That cancels with that negative. And so if you compress the piston, then work is being done on the system and W would be positive.
A gas confined, such as the gas in this cylinder, exerts a pressure on the surfaces that confine it. Pressure is a measure of the force exerted on a unit area. The pressure confining the gas in the cylinder is measured by the force on the piston per unit area. When a gas expands, it does work against the surroundings. In this case, the gas does work by lifting the piston. The work done is given by the force exerted times the distance over which the force operates. In the expansion of the gas, the force is exerted over the distance shown as delta H. The work done is given by the product of the volume change times the pressure. The pressure might be kept constant in such an expansion by heating the gas continuously as it expands. If the pressure is not constant, the formula is still correct, but pressure must be evaluated at each stage of the expansion.
And so again, for expansion work, it's equal to minus P delta V. And for this case, we assume that P is constant. And so if we imagine that we start here and we want to get to there. Now, for this path here, delta V is not changing, and so W is 0. Now you can imagine that you can do this by cooling it, so Q would be negative. Now if we go from here to here, now we're increasing the volume, and the pressure is constant, and so it'd actually just be 1.2 atmospheres times our change in volume, which actually corresponds to the area under that line. And so work would be equal to minus area. Now you're expanding it, and so the system is doing work, and so that would give you a negative number. Now it turns out the amount of heat that was added was equal to the negative amount of work done, and so your delta U for this case was actually equal to 0. And so if the piston expands, it's doing work, W will be negative. If the piston contracts, work is being done on the system, and W would be positive. Now, we can also go with a reversible process, and again, the work done on system would correspond to the area underneath the curve. And so for this case, we'd actually think about it in small steps. And we could actually calculate W for each of these steps and then add them up. And so I have this problem. A 100-watt electric heater operates for 20 minutes to heat the gas in a cylinder. At the same time, the gas expands from 2 liters to 52.5 liters against a constant atmospheric pressure of 0.975 atmospheres. What is the change in internal energy? And so change in internal energy is equal to Q plus W, where Q is heat added to the system and W is work done on the system. So we can actually calculate the W first. Now, our pressure is given in atmospheres. And so we actually want to convert from atmospheres to pascals. And so 1 atmosphere is equal to 1.01325 times 10 to the 5th pascals. Now, the reason that we want to convert to pascals is because then it'll be much easier to convert it into units of energy. And so 0.975 atmospheres, multiply our conversion, the atmospheres cancel, and that leaves us with pascals. And then 1 pascal, again, is just equal to a kilogram per meter per second squared. And so our change in volume was 52.5 liters minus 2 liters, and that gives us 50.5 liters. Now, if you notice on the pascals, it's kilogram per meter per second squared, and so we probably want the volume, the change in volume, in cubic meters. And so we have liters, and 1,000 milliliters is equal to 1 liter, and so liters will cancel. A milliliter is equal to a cubic centimeter, and so milliliters will cancel. And 1 meter cubed is equal to 10 to the 6 cubic centimeters, so cubic centimeters cancel. And so if we multiply this out, we get the change in volume is equal to 50.5 times 10 to the minus 3 meters cubed. And now we have P delta V, or minus P delta V. We calculated our minus P here. Again, that was in pascals. And we just calculated delta V in terms of meters cubed. And so that meter will cancel with one of those meters, and we'll be left with kilogram meter squared per second squared, which actually is the same units as a joule. And again, because we're doing an expansion, W will be negative. And so our W, we get basically minus 5 kilojoules of work is being done by the system on the surroundings. Now for Q, we're told that we had a 100-watt heater, and a watt is equal to a joule per second. And we're told that it works for 20 minutes. There's 60 seconds per minute. And so the minutes cancel and the seconds cancel. And so we're left with just 120,000 joules. And so change in internal energy is Q plus W. So 120,000 joules for the heat minus 5 kilojoules for the work. And we get the change in internal energy is equal to 1.15 times 10 to the 5th joules. And so when you're going from one state to another state, you can calculate both Q and for W. And so for these two changes, our initial state is the same, 3 atmospheres and 8 liters, 3 atmospheres, 8 liters. And our final state's the same, 1.2 atmosphere, 20 liters, 1.2 atmosphere, 20 liters. But our paths are very different. Right, I think this is the one that we talked about earlier, where we saw that W is equal to minus 1.46, and we saw that Q was equal to plus 1.46. Now that corresponds to a delta U of equal to 0. Now for this path, notice that W is equal to minus 2.2 kilojoules, and Q is equal to plus 2.2 kilojoules. So it's kind of interesting. We have exactly the same final initial states, but notice that Q and W are not the same. And so we call Q and W path functions because they depend on the path. The change in internal energy does not change. And so we just call internal energy a state function because the change in internal energy only depends on the final initial states, doesn't depend on the path. Q and W does depend on the path. And so it's much easier to deal with a state function because it doesn't depend on the path you take. The change in state function only depends on the final initial state. Q and W, heat and work in general, are path functions, not state functions. Now it's kind of interesting. If we start with the equation that we had for the first law, delta U is equal to Q plus W, change in internal energy equals heat added to the system plus work done on the system. Now if we assume that we have only expansion work, and we saw that for expansion work, W is equal to minus P delta V. Now notice with this assumption, that's assuming W is a state function, right? So in general, W's a path function. But if we're saying that the only work is expansion work, then we're changing it into a state function because on the right-hand side, these are just states as long as P is constant. So if you assume constant pressure and expansion work, that makes W a state function. And so if we plug it minus P delta V here, now if we solve for Q, you notice Q equals this, and the right-hand side of this equation, those are all state functions as long as P is constant. So if we have constant P and only expansion work, that makes W a state function. And now we're seeing that constant P and only expansion work makes Q a state function. Now that's important enough that we actually give this a new name. And so Q, assuming constant pressure and only expansion work, is defined as the change in enthalpy. And to me, the best definition for enthalpy is right here. The change in enthalpy is equal to Q, assuming expansion work and constant pressure. And so most chemical reactions take place in open containers, hence occur at constant pressure, about 1 atmosphere. And so enthalpy is a state function that allows us to keep track of heat transfer at constant pressure. And so enthalpy is a state function, internal energy is a state function. Q and W in general are path functions, but if you make the assumption constant pressure and expansion work, both heat and work become state functions. And so if heat is transferred to the system, then delta H final is bigger than delta H initial. Delta is always final minus initial, products minus reactants. So if heat is transferred to the system, that means Q is positive. That means delta H is positive, and we refer to that as an endothermic process. And so again, you can imagine initially our enthalpy is down here. We add heat, and our enthalpy goes up there. Delta H is products minus reactants, and so that would give us a positive delta H. Evaporation is always endothermic. If you want to go from a liquid to gas, you always have to add heat. And so in endothermic processes, heat can be treated as a reactant. And you should remember that gas is always the most stable phase at high temperature. Now, liquid to solid is always exothermic. And so if you want to go from a liquid to solid, you have to take heat away. That's how the freezer works. And so for exothermic process, heat is always a product. And so liquid has a higher enthalpy than the solid. And so our delta H would be negative. And so for exothermic processes, delta H is negative. For endothermic processes, delta H is positive. And you should also remember that solids are typically the most stable phase at low temperature. And so endothermic processes, heat is added to the system, delta H is positive. Heat goes from the surroundings to the system. Remember, the universe is just the surroundings and the system. For exothermic processes, heat is removed from the system. So heat will be a product, delta H will be negative. And heat goes from the system to the surroundings. Again, remember, we define the system such that the only thing that can be transferred between the system and surroundings is heat and work. And so, in terms of a reaction, we can write our delta H here. But we see delta H is positive. That corresponds to heat being a reactant. For exothermic reaction, delta H is negative. So we could write it this way. Or we could actually include the heat explicitly in the chemical reaction. Now notice that this reaction here is that one written backwards. And so if we flip the product's reactants, that actually changes the sign of our delta H. If this reaction here is endothermic, if we flip it product's reactants, then we actually make it an exothermic reaction. Now, if we multiply a reaction times 2, we also have to multiply the delta H times 2. And so if this reaction takes 285 kilojoules of heat, if we multiply the reactants and products by 2, we'll need twice as much heat. And so if you flip a reaction, it changes the sign of delta H. If you multiply the reaction times the number, you also have to multiply the delta H by that number.
The water on this cork pad will freeze when an endothermic reaction absorbs heat from its surroundings, including the water and cork. The solids barium hydroxide octahydrate and ammonium thiocyanate absorb heat as they react, forming barium thiocyanate, ammonia gas, and water. A slurry forms as the two solids begin to react, because one of the reaction products is water. The waters of hydration are also released, forming an aqueous solution that allows the reaction to proceed more quickly. The temperature of the slurry drops to minus 15 degrees Celsius. The water between the cork and the beaker has frozen. Atmospheric moisture has also condensed and frozen on the side of the beaker. Reactions are either exothermic or endothermic, meaning that energy as heat is either released or absorbed.
And so it's kind of cool. They put water between the cork and the beaker, and then the beaker got cold enough that actually caused the water to freeze. Now, if you do a reaction and the beaker gets cold, that means that's a endothermic process, because if the beaker's cold, that means heat will be transferred to the beaker. Remember, heat goes from the hotter thing to the colder thing. And so if your beaker's cold, that means heat will go to the beaker. And so that corresponds to an endothermic process. And so this was endothermic. Now, if the beaker's hot, then heat will go from the system's surroundings, and that would be an exothermic process.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product-favored.
And so the test tube got very hot, and so heat's going from the system to the surroundings, and so that would be an exothermic process. And so going from gummy bear to liquefied bear, the gummy bear has a higher chemical potential energy, higher enthalpy, and then during this reaction, you're going to release a lot of heat. And so again, exothermic process, and the liquefied bear will have a lower enthalpy. Also would have a lower chemical potential energy. In general, reactions that transfer energy to their surroundings are product favored, but not always. So hopefully you can describe how energy can be converted from one form to another form. You should be able to describe how the universe is separated into the system plus the surroundings. And again, it's really important to remember that the only things transferred between system surroundings by this definition is heat and work. We're defining the system as a closed system. You should be able to calculate the change in internal energy of the system, Q plus W. Hopefully you know that delta H, the change in enthalpy, is equal to heat transfer to the system under constant pressure and expansion work. So if you make that assumption, then Q and W actually become state functions. You should be able to describe how enthalpy and internal energy are both state functions. And again, state functions are nice to deal with because they only depend on the final initial change. Their change depends only on their final initial state. And remember, exothermic means heat's transferred from the system to the surroundings. And endothermic means that heat's transferred from the surroundings to the system. I hope that helps.